All right, ladies and gentlemen, so this is the midterm walkthrough. Tell me what category variable each variable is, and then what type within those two categories the variable is. So sex is categorical. Nominal. Right? You can put an order to it. It's not males before females or females before males. Age, numerical. And here I'll take discrete or continuous. Race, categorical, nominal. Height, numerical, continuous. Weight, numerical. I'll take discrete or continuous. The reason why I'm saying continuous here is because it has decimal points. The gene is categorical, nominal, and the last one is numeric, continuous. If I give you a set of 2,000 numbers with no outliers, how would you describe the measure of central tendency? No outliers, mean. Right? Because you remember when a distribution and the mean is the same as a median, go with the mean. Outliers will draw the mean away, but the median will probably stay the same. So no outliers, go with the mean. In describing the household income of Fairfax County, we often use median instead of mean. Why? Because of outliers. And then, it just explained to me that what outliers do, they move the mean around, but they don't do the same for the median. What is the probability of rolling a 10? So this one I actually did in one of the quizzes. Remember that? So this is 2. This is 3, 4, 5, 6, 7. This is 3, 4, 5, 6, 7, 8, 9, 10, 10, 10. 3 out of 6 times 6, 36. Or 1 out of 12. And you can use Bayes' theorem to figure it out as well, but this is the simplest way, just to think it through. Explain to me why the positive predictive value of a screening test increases as the prevalence increases. Because when we do the true in the test is positive or negative, true is disease or no disease, right? And prevalence is, if this is A, B, C, D, this is A plus C, B plus D, A plus B, C plus D. Prevalence is A over A plus C, or how many people do have the disease out of the total number of people. I'm sorry, no, it's not A over A plus C. As soon as I said that, I realized my mistake. It is the total number of people, A, over A plus B plus C plus D, over the total number of people. So total number of disease over the total number of people. So as prevalence increases, then this number is increasing. And what is positive predictive value is A over A plus B. So if A is increasing here, it's going to increase here, it's going to increase here, and this number is going to be increased. it's going to increase here. Okay? So that's how you do this. That's how you reason through this. You can also reason through it mathematically, right? You actually use the formula. Prevalence is equal to A or A plus B plus C plus D. And PPV is equal to A over A plus B. What is the chances that somebody does have the disease when they test positive? These are all the positives. And so then you just plug in any random numbers in here, and you'll get the same results. That as A goes up, because prevalence is going up, then this number is going to get bigger. And this number is actually, this proportion here is actually smaller than prevalence because you're not accounting for these numbers over here. Or rather, it's going to be larger because this fraction is going to be larger because you're not accounting for those numbers there. Okay. So the Poisson distribution has possible values between 0 and n possible events. Why doesn't it have a negative value? Because we're talking about counts of events. And you cannot say that you had -3 kicks by a horse. Or that you had -3 homicides. Right? That doesn't make any sense, and that's why you don't have any negatives. What are the mean and the variance of the Poisson distribution? They're the same. And finally, if I'm calculating a Z-score, or just rather the S, why do I know if it's negative? And the value I'm standardizing this in the mean. Sorry. What do you see minus what you expect over S? It's late at night, guys. It's almost 11 p.m. So if this number is less than the mean, 3, and the mean is 5, then I'm already going to get a negative number up here, and that will turn the whole thing negative. Okay? It's just how fractions work. That's all I was looking for you guys to know the formula and to figure out how fractions work. Because remember, that'll lead you down the path that you'll know if you have a negative z, you're looking for something over here on the left. Suppose Fairfax County school system wants you to determine percentage of students who use cigarette and or smoke. Tell me which of the following studies would you conduct. Remember, a population is all the students. The sample that I'm looking for has to be random. And whatever I do to the sample as far as testing has to be generalizable. And so which ones are these? You go to a football game between the biggest high schools and count the number of students you see smoking using a cigarette. Then use that number. No, because it's only the biggest high schools. What about the smallest high schools? That's not representative of everybody. You go to the hospital and look at the medical records of all the students who were brought in with lung injuries from using cigarettes. You then use that count of students to extrapolate the number of users. No, because we know that not everybody who gets injured, not everybody who vapes gets injured. You conduct a random survey of students and ask them if they use e-cigarettes or smoke. You then use the results. Yeah, so I randomly, right? And then the last one, you put out a bunch of cigarettes and e-cigarettes and count the number of students who take either one over the course of the year. This is your number of students who use them. Nope. Randomness is the main thing that I was looking for here. The formula for the standard error of the sample mean, right? What happens to the standard error as n increases? So if this number increases, as n goes up, then the standard error goes down because a bigger denominator leads to a smaller fraction. If n is equal to the size of the population, what is the standard error? Well, the standard error then is equal to S, the standard deviation of the population. Okay. If you're sampling over and over, but your samples are all the same size as the population you're sampling from, is there a standard error? The answer is no. Explain or interpret for me in a few sentences the following mean, standard deviation, 95% confidence interval. So I wanted you guys to say something like, when I took all the values and I divided them by the total number of values, I took all the values and added them and divided them by the total number of values, I got the number 57. Repeated sampling of the of the values led to some means of some samples being 57, others were 60, others were 54, but the standard deviation was always 3. I am 95% confident that the true mean in the population is somewhere between 56.8 and 57.2. That's it. What other bit of information would you need to know to calculate the 95% confidence interval? Remember the 95% confidence interval Z, the critical Z, so it's the mean plus or minus the critical C times the standard error. And we know the standard error is that over that. So I have the mean, I have the standard deviation, I have the 95% confidence interval itself. I know that the z-score for that is 1.96. So I have that. All I'm missing is the n. Okay, so if a basketball player is normally distributed with a mean of 2.01 meters, standard deviation of 12 centimeters, what is the t-score of a sample of 50 players? Degrees of freedom will be 49, right? Mean is 2.37. Do we have everything we need for getting the t-score? And what is reject or fail, the null hypothesis? The null hypothesis is that the player, that the mean, the null hypothesis is that the mean is equal to the population mean, right? And so we should be 95% confident that the mean is within, that the population mean is within a certain distance, 2 standard deviations of this. So let's do this. And so the critical t value that I'm looking for, if I look at the t table, I don't have a degrees of freedom of 49. The t table that I have online tells me that it's somewhere between 2.02 and 2. Excuse me, I have a little bit of a sore throat today. I was talking too much yesterday in another lecture. But if I go to an online calculator, it tells me that it's 2.01. Or if I use R, then I use R and I do this QT parenthesis C parenthesis 0.025 comma 0.975 parentheses DF equals 49 parentheses. Then the answer that R gives me is negative 2.009575 to 2.009575. So this is what I'm telling it is, I want you to tell me the t-scores here and here. So this one's going to be negative, this one's going to be positive here and here, where I have 2.5% here and I have 2.5% here. And because I have 2.5% here, then I'm going to have 97.5 here to the left. And so that's the value. So you see from the table, it's pretty close. From the online calculator, it's pretty close. This one is the one that I like from R because it is much more precise. So we just do our calculation, right? We do this. Let's get another color. And it's going to be 2.37 minus 2.01. So I already know it's going to be to the right. And then I do it over the standard error. So the standard error is going to be the standard deviation, 12 centimeters, 0.12, right? Divided by square root of n, so 50. And so then we continue. I'm going to keep it going over here. 2.37 minus 2.01, 0.36 over 0.12 over square root of 50. Let me use my calculator. Let's see, clear 50. What is your square root? 7.07. 0.12 divided by 7.07 is 0.36 over 0.017, which gives me a crazy t-value of 21.176. So if I were to draw this out, when in doubt, draw it out. Let's make a better one like that. And I'm saying that my mean here is 2.01. Then where does 2.37 lie? And we know that it's way out there. It's at least 3 standard deviations, right? Because 12 centimeters, so it's 36. So it's 3 standard deviations out. It's out here somewhere. And it's so far out that the t-score is 21.176. And so even without knowing this, you know it's going to be way out there. And so I reject the null hypothesis that these are the same, because it is more than 3 standard deviations. It's a very unexpected mean height. Okay, for 50 players, it would, if you have an NBA team or something and the mean was this for all the teams, and all of a sudden you had 50 players show up with this mean, woo, yeah, very, very tall, very tall. Okay, so if I tell you the confidence interval of a poll is 45 to 51, I am 95% confident that the true approval is somewhere between 45 and 51. Do I feel comfortable? And this one I leave up to you guys, because you can tell me something like, yes, I feel comfortable because I am 95% confident that it is somewhere in there, and because 50% is in there, then I would feel comfortable with that. On the other hand, you can say, no, I don't feel comfortable because it's a range of 45 to 51, and 50 is somewhere over here. And there's a really good chance that it's somewhere to the left as well. So I leave it up to you. What would you need to know about the poll before you can say half all voters, not just those polls, approve or agree? I would need to know if the poll was the sampling, was it random, right? Half of all voters, not just those who were polled. This goes back to that other question about the vaping. What would you do to the poll to be more certain as to the real percentage of people who approve or agree with the political decision? So I would want to have a shorter confidence interval, right? And to get a shorter confidence interval, what do you need to do? You need to increase the sample size. Remember, if you increase the sample size, you get a smaller denominator. And when you get a smaller standard error, remember 1.96 times the standard error. When you get a smaller standard error, then you get a smaller number here in the plus minus, because this is equal to the margin of error. And when you get a smaller standard error, you get a smaller margin of error. Okay? This one, if you guys were paying attention, this one is the one that I mentioned in one of the lectures. So you just have to listen to the lecture. The answer is there. So the evidence of a study where 450 people drank coffee, and then others who did not. And so there were patients at an emergency department in 1989. The results show greater odds of pancreatic cancer in those who drink coffee, greater odds of cancer. Something that doesn't seem right, so you ask the researchers controlled for smoking in the two groups. In this scenario, tell me which variable is the outcome of interest. So I have two variables, right? I have coffee drinking, and then I have smoking, and then I have the last variable being cancer. And so the theory here is that drinking coffee leads to cancer, but you, being the smart epidemiologist, will tell me that smoking leads to cancer, and that smokers drink more coffee. And so here then, smoking is acting as a confounder. And so we need to adjust for this, right? We need to then create 4 categories. We need to have coffee drinkers who smoke. We need to have coffee drinkers who do not smoke. we need to have non-coffee drinkers. You get the point. Who smoke. And non-coffee drinkers who do not smoke. And here we need to look at their odds, compare those groups. And then that'll tell us if it's the smoking or if it's the coffee that's causing the cancer. Because if it's the smoking, then you'll see increased odds here and here. And if it's the coffee, then you'll see it only here. And if it's neither, all will have equal odds. The exposure then is coffee or smoking. The outcome is cancer, and the confounder is smoking. What kind of study was conducted? This is just looking at case control. It's what we do when we study outbreaks. Just a case control study. You can also call it an observational study. They didn't give people coffee and the other half no. It's an observational. It's an experimental case control. Whatever you want to call it, as long as you gave me a good explanation of how they conducted this. Okay, in the U.S., people who develop high blood pressure also tend to be overweight or obese. Is obesity independent of high blood pressure? 30% of Americans are obese. 40% have high blood pressure. HBP. And 40 have both. Right? And so if it's 40 for both, then we know that these numbers need to be a little bit lower here. I'm just theorizing it, guys. I don't want you to go too crazy on this. So I can already tell you that it's not independent, right? It's not independent because that wedge in the middle exists. So, that's how you answer that. Or you can also say that the probability of obesity times the probability of high blood pressure is does not equal the probability of both. And that's what makes it not independent. If they were independent, then these two would be that this would work. So if 40%, that leaves 60%, right? So we work this Venn diagram. So what I'm going to do is I'm going to erase it all. Just do it all over again. All right. So I have obesity and high blood pressure. And I know that 40% have both. This represents 100%. So then I'm going to have 60%. I'm going to have 60% to go to the two sides. All right. So that's the answer. What percent of Americans are neither obese nor hypertensive? Boom. Because if no, this is either obese or hypertensive. This is the two of them, and this is 100%. So I have 60%. 30% are obese. 40 have high blood pressure. 40 have high blood pressure and obesity. And so here, 30 and 30 works perfect. Right? And what percent of Americans are neither obese nor hypertensive? That would be 0%. I'll take that. You can work other things, right? Because this could be 40 and 40 and 20. Or you can say 40, 40, and 15, and then this would be 5 for the ones that are neither. So I leave it up to you. This is a very open-ended answer, and you can use the formulas, but I just wanted you to theorize and to draw this out and think about it. Suppose you toss a fair coin 12 times. What is the probability of getting exactly 7 heads? So here we're talking about the in the binomial the probability that an n trial binomial, so how many trials do we have? We have 12 trials, will give us exactly x successes, so exactly 7 heads, and the probability is 0.5, right, because it's a fair coin. And then you can plug it into your calculator. Okay. So that would be the binom for, sorry, not for, 7. The binom 7 size is equal to 12. Probability is equal to 0.5. Similarly, we can use p binom. Seven size equal 12. Probability equals 0.5. And what R gives us is 19%, 0.1933594, or 19.3%. And this is exactly 7 heads throughout the thing. If I were to ask you, if I were to ask you 7 in a row, that's a whole other thing, right? Because you would have to get the probability of 1, right, being heads, and then add it times the probability of the next one being heads, and the probability, and then get that going. The probability of all of them, well, you just replace 12 in here, and that is let me see here, because I'm using R. Very small. It is 0.00024, or 0.024%. Probably of none of them being heads. Then I go in and put a 0 in there. And guess what? It's the same, because we are talking about this distribution, right? So what's the probability of all 12 being heads? It's out here somewhere, and all 0. And then the probabilities are in the middle, where your mean, because of 0.05, it's going to be 6. All right? And that makes sense, that the 7 would be somewhere over here. Okay? Screening test for influenza has a sensitivity of 99%, specificity of 92%, 10,000 patients, prevalence is 5%. A person who tests positive as a physician, how likely it is that they have real influenza. So this is that setup, that 2x2 table. Okay? Test positive or negative. Truth is disease or no disease. Right? And we're talking about 10,000 people, and with a prevalence of 5%, so 500 people will have the disease, 9,500 people will not. 99% sensitivity, so 99% of this, which is 495, and then 5 here. That's how we set up sensitivity. 92% specificity, so 95 times 2, 190 will be, sorry, no, not there. No, 92% specificity. So it'll catch 92%. Yeah, so 190 will be up here. Is it 190? I'm not using my calculator right now. Yeah, 190. So sometimes I do it in my head and I don't quite get it right. So then 9,500 minus 190. 0 minus 0 is 0. 10 minus 9 is 1. 5 minus 2 is 3. 9310. Okay. And then we have 685 who test positive, and 9,315 who test negative. All right, and you guys at home do the math. This should add up to 10,000, and this should add up to 10,000. So a person who tests positive, one of the 685, as a physician, how likely it is that they really have influenza. 685. 495 out of the 685 really do have influenza, so this is positive predictive value. And then that will be your answer for this question. What do we call the certainty of a physician can have that a person who tests positive really is infected with influenza? Positive predictive value. That'll give you that answer. Okay? If an exam has an average score of 92 points with a variance of 9 points, okay, variance of 9 points, variance, not standard deviation, variance. So the square root of the variance is equal to the standard deviation. So the square root of 9 is equal to 3. So S is equal to 3. Okay, make sure you didn't make that mistake. What score does a student need to get to be in the top 10% of the class? So 92, right? And to be in the top 10% of the class, so you have 10% over here, or 0.10. So the question that I'm asking here is, what is Z, right? Because I don't tell you how many students there are, so that's why you need to use Z. The Z score for 90%, and that is where you go to that R code that I sent you guys. And sorry, my recording kind of jumped, but if you go to the Z score, that R code that I sent you, the Z score for 90% is 1.82, and so then you plug it into 1.82 times the standard deviation of 3, and this will give you the response for 10% of the class. And then you do the same. Now you're looking at 70% to the left for the second question, and that score is 0.544, and that'll give you the answer for that. And then the last answer, what I'm going to do is I'm going to go ahead and redo it for you guys. And again, I apologize, my recording thing here jumped. So here I'm looking at, again, 92, and the question, where is 80 on the Z scale? So 92 on the Z scale is 0, and what is it on the what is it for 80? So remember, 80 minus 92 over 3. So that's negative 12 over 3, which is negative 4. So it's a negative 4 over here. Very, very small number. Most everybody passed. It's actually less than 0.01. Okay. So I'll take that answer, or you can actually do it in R and get the probability. Z score to the left is negative 4. Z score to the right is 4. Actually, you can just change Z score 4. And then Z score to area under the curve is where I have it on the AR code. And you just do it. And area to the left is, yep, less than 0.001. Area to the right, yep. Super tiny, super tiny. Along the same lines as the previous question, you know, we're going to compare two players, and so we need to standardize their scoring. Okay, so for basketball, I'm going to say NBA, but it could be any league of basketball. Average of 28. And so mean of so it's 22. So let's do. Okay. Basketball player has 28, but the average is 22, standard deviation of 4 points, and that'll standardize him. And then the MLB player has a batting average of 0.255 when the rest of the league has 2.40. So they're both exceptional. They're both good. And a variance of 0.049. Again, variance. Remember variance. The square root of variance is S. And so the square root of 0.0449 is 0.07. And so S is equal to 0.07. And then you do the calculations and you get Z scores, right? So this one is minus 6 divided by 4, or 3 divided by 2, or 1 1/3. And this guy is 15 over 7. So we're going to say 2 something. 2 something. I don't want to keep stopping and getting the calculator, but I hope you guys did for the exam. So going strictly on batting average and points per game, this guy would be the better, because he's higher on the ranking, right? He's higher on the ranking than the NBA player on the Z score, right? The MLB player is here, whereas the NBA player is here. So the MLB player has more players under him than the NBA player does. And that's how you explain your answer. You're just saying the MLB player excels compared to his peers versus the NBA player compared to his peers. Maybe that'll settle the LeBron and Michael Jordan question. And then for this one, you're just going to use the R code, okay? So just use the R code. I can tell you just from knowing what we know about the Z distributions, this is 50%, right? On the Z scale, this is a 0. We know that 1.96 and negative 1.96 have about 2 standard deviations inside, but they're 95%. Right? So this is to the left is 0.025, and to the right is 0.025, and in between the two of them is 95%. So that's that answer there. P-value to the left of that guy is 97.5%. To the right is 2.5%. P-value to the left of this guy of -3 is less than 0.01, and to the right is about 1. Not quite 1, but about 1. I'll take that, or I'll take whatever number you come up with that is close to that. Same thing with 0.05. So we know that I'm not 0.05, 0.5. So z-score 0.5 on that handy R-score, that R cheat sheet that I sent you guys. Area to the left, 0.7, 70%. Area to the right, 30%. 1 and 1. Area to the left, 84%. 1 and 1. It should have been -1. Oh, my goodness. I won't take any points off for that one. Don't worry about that one. Again, going back to that question, we have on the normal scale, 2.01 meters, which on the Z scale is 0. So where would 1.5 meters be? Where would 1.65 be? Where is 2.25? And where is 2.01? So 2.01 is neither. It's average. This is probably unusually high because we kind of found out that one, the last one, right? Unusually. And what I'm getting at is 2 standard deviations. So anything between minus 24 centimeters to plus 24 centimeters. So 2.25, unusually high. Minus 24 centimeters, these two guys are also unusually short. Okay, so here I don't want you to get too bogged down. I just want you to know the formula for this is 43 plus or minus 1.96, right? This is going to be for the 95% confidence interval. Why 1.96? Because that's a C-score for 95% confidence intervals times the standard deviation of 3 over the square root of 10,000. And when you use this high number like this all is very small, and this all is very small. So it's actually it's 42.9 to 43.1. So you are 95% confident that the true mean of the population, the true mean age of the population is between 42.9 and 43.1. What do you do for 99%? 43 plus or minus 3. Let me check this in there. Yep, 3. And so it's just about the same, because again 3 over this, it's very small. It's very small. So and the calculator gave me the same, 42.9 to 43.1. And that's what I wanted you guys to see, is that because of this very, very high number of people over here, the two are about the same. So you would answer in a sentence, I am 95% confident that the true mean age of the population is between 42.9 and 43.1 based on a sample of 10,000 people. How can you make it even tighter or smaller? More people, but you're gonna get like 43 to 43, like, or 42.9999 to 43.0001. Right. This is a good sample size, and it goes back to what we were talking before about sample sizes. And the last one that we're going to look at, the R code, I am going to just create it independently. If there's anything outstanding, I'll let you guys know. But I was looking at it, and a lot of you did the right thing, so we're good. The average age of a person in a town with that many residents, average age is 56. Standard deviation of 2 years, 230,000 people. One business claims to be very inclusive. You ask the business for a list of ages of its employees, and the mean age of all employees is 34. Minus 56 over the standard deviation, which is 2. Right? We're not going to do square root of n of that, right? Because that's not the sample. This is the population size, and we don't know the sample size that we're using, so we're just going to keep it at that. Okay, so 16 plus 6 is 22 over 2. Your z-score is 11. Right, and if the average is 56, z-score of 0, then, sorry, z-score is negative 11. Then negative 11 over here. That's very, 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 very small chance. It's well outside of your 95% confidence interval. Just not. You don't need to do a test. You just need to say, look, they're very young. This is very young compared to the rest of the population. There's a very small chance that there's a very small probability that just by chance alone, you got this sample. Okay? What kind of confunders or bias might be at play? Maybe this is hard work that needs people who are young. Maybe this is something related to technology that older folks have not adopted. Maybe, when they put the announcement out for jobs, they only send it out through social media, and only the younger ones applied. Just think about it. No need to write an essay, just that. And so that ends this. If you have any questions, comments, concerns, you know how to reach me. I will post the R code later. You all did great. Good job. We're almost there.